Mare Ingenii, Latin for Sea of Cleverness, is one of the few mare features on the lunar far side. The mare sits in the Ingenii Impact Basin, which in turn sits in the northwestern section of the massive South Pole Aitken Basin. The darker material in Mare Ingenii and the surrounding craters is of the Upper Imbrian epoch. The dark circular feature which dominates the basin is the crater Thomson. It has a diameter of 112 kilometers or 69.5 miles. Through laser altimetry, we can see that Thomson has been flooded with lava, leaving only remnants of the crater rim. Just to the south is Thomson M. It has a diameter of 100 kilometers, or just over 62 miles. Thomson M is the location of an interesting discovery. We now zoom down to the surface and enable the Lunar Reconnaissance Orbiter narrow-angle camera layer. This high-resolution camera allows us to see the collapsed lava pit in greater detail. The pit measures about 130 meters, or 426 feet in diameter. Researchers speculate that the pit could be a skylight resulting from the collapse of the roof of a lava tube. The accessibility and extent of the lava tube have yet to be determined, and such lava tubes are of great interest as potential locations for lunar bases, offering protection from extreme swings in temperature, galactic and solar radiation, and meteoroid impacts. Lunar swirls are among the most beautiful and bizarre features on the Moon. Seen as bright, sinuous regions, swirls are associated with weak magnetic anomalies in the Moon's crust. By toggling the laser altimetry on and off, we can see that the swirls bear no obvious relation to topography, but are just regions of higher albedo. Lunar swirls are believed to be associated with stronger than normal magnetic fields which deflect solar wind. This lessens space weathering, resulting in the higher albedo. Other theories suggest underground flows of magnetized lava, a cometary impact, or the convergence of seismic waves from massive impacts. The impact model points to observations that some of these anomalies are antipodal, or directly opposite, to the younger large impact basins on the Moon. The antipode of the Ingenii Impact Basin is the Imbrium Impact Basin. The convergence of seismic waves from the Imbrium impact, along with heavy cratering around the basin, played a pivotal role in reshaping the landscape. The furrowed crater walls of the basin, and possibly those of Van de Graaff crater, may have been caused by focused seismic waves. Van de Graaff has the appearance of two merged craters, approximately in a figure 8 shape, with no intervening rims separating the two halves. The southwest section of the crater also contains swirls and a prominent central peak. Just to the northeast is Van de Graaff Q. It has a diameter of 15 kilometers, or 9.3 miles, and a depth of 2.24 kilometers, or 1.4 miles. Notice the slump inside of Van de Graaff Q caused by the impact of this undesignated crater. The northeastern section of Van de Graaff is slightly smoother in form and has a subdued central peak. Van de Graaff C is 20 kilometers or 12.4 miles in diameter. To the southeast of Van de Graaff is Leibniz. The crater has a diameter of 245 kilometers or 152 miles. The outer rim is roughly circular with a prominent outward bulge along the southern face. Much of the interior floor of this walled plain has been resurfaced by lava, leaving a level and nearly featureless surface. However, the southeastern part of the floor is more irregular because ejecta from Finsen covers part of it. The crater floor also contains swirls, as well as ejecta rays from Finsen. Swirls can be found in other locations on the Moon, such as Reiner Gamma, and as seen here in Mare Marginis. The Ingenii Basin provides valuable insight to the composition and geological history of the Moon's far side. The region is considered to be a potential target for future lunar missions due to its unique features and scientific value.